How many people came up with numbers at the end? Okay. Yeah, I got a letter. D minus. Um, the first step is to draw a free body diagram, and in this case, there's no thinking about what to isolate because there's only one body. So here's our object. And I'm going to fill out that table. And to fill out that table, you need to break things up into vector components. Bless you. And to fill things out in vector components, you need to choose a coordinate system. So I'm going to put my coordinate system here. I'm also going to put my about point there, but you should keep in mind that there's no reason you have to put your about point at the origin. You could put it anywhere you want, but a lot of times it makes the math simpler. So what loads do we have? Well, there's a force due to gravity, and then there are forces wherever anything's touching. We know there's a force here, right? So I'll write that one in right now. So 1,000 newtons there. And then there's a force due to gravity. That acts right at the center of mass, going down, and it's 981 newtons. And then there are forces where anything's touching the object. So there's some kind of load, or I should say loads. Sometimes it can be a couple as well, right? But in this case, what kind of loads are applied by a pin joint? What?
Did you say allowed bar?
Yeah, what kind of are applied?
2D force?
Yeah, a full force vector is applied by that pin joint, a 2D force. So I'll write that like this, and use that convention that says this vector is the force on the body by the pin. And then where else is something touching this object? Cable, yep. And since I'm going to specify the direction like this, so I'm not going to use, that means that I'm going to have a scalar variable, so I'm not going to use that sign convention, that naming convention, so I'll just call this tension, okay? So there's a complete free body diagram. Anybody have any questions about that or do anything wrong that you want explained? Okay. Okay.
But using the rotational second law, if you chose your middle point
Yeah.
and did everything about it, you lose the weight.
That's right. You lose the weight and the tension force in your moment equation. That's totally correct. Yep. I chose it here, and then in our moments we lose that FBP. So you gain something and lose something in either case. Okay, so let's fill out that table. So there's where the force is applied, the about point, the row vector, the force vector, and the moment about A. I didn't think ahead where I drew this, but don't worry. Okay. So let's start with that force FBP, the force on the body by the pin. Where is that applied in our coordinate system? 0, 0. Oops. And for an about point, I said I'm going to choose the origin. But so you'd get different numbers if you chose a different about point, but your final answers will be the same. So 0, 0. And once you choose your about point for the first force, that's going to be your about point the whole way down, right? So rho then is 0, 0. The force vector is F BPX, F BPY. And your moment is 0. Second, let's do that gravity force. Where's that applied?
0.3536.
Yeah. 3536 for both. And about point stays the same. So rho is 0.3536, 0.3536. Your force vector is 0, negative 981. So your moment is 0.3536 times negative 981 minus 0. And you get, I think, if you're like me, you get 346.88 negative. Now the tension force, that's applied at the same point.
Work out the same if you put tension and gravity together and just say the point of the middle points.
Put them together and call, like add up.
This would be X and Y in this.
Oh yeah, sure, that'll work fine.
Right?
Yeah, that's right. So about point is the same, 0, 0. So the rho vector is the same. The force vector is negative t, 0. So you get 0 minus negative 0.3536 t. So you get positive 0.3536 t for the moment. And then the last force is this one. And this one actually is calculating that moment is pretty simple if you think of this as just a perpendicular distance from the force. But I'm still going to fill this out. You'll get the same thing. We know we should get a moment about this point of 1,000 times 1 meter clockwise, so negative. This force acts at, bless you, 0.7071, 0.7071. About point is the same. So rho vector is 0.7071, 0.7071. The force vector is positive 707.1, negative 707.1. And so you have negative these two minus these two, and it gives you negative 1,000. Any questions so far on that table? Okay, so Newton's second law says, and we just go down the force column, FBPX, FBPY plus 0, negative 981 plus negative T0 plus 707.1 negative 707.1 is equal to 0, 0. And rotational version says 0 minus 346.88 plus 0.3536t minus 1,000 is equal to 0. Okay, so that gives us these three equations. I'll rearrange some stuff to put it in matrix form. So negative t plus f bpx is equal to negative 707.1. Then we have f bpy is equal to negative, is equal to positive 1688.1. And then third, 0.3536t is equal to positive 1346.88. So if you write that in a matrix form, you get negative 1, 1, 0, and the order of the variables is t, f, bpx, f, bpy is equal to negative 707.1. This one is 0, 0, 1, 1688.1. And this one is 0.353600, 1346.88. Any questions up to there? And if you solve that, what I got was t is equal to 3809.05 newtons, and f bp as a vector is equal to 3101.95, 1688.1. Anybody get all the way to those answers? Bearing in mind, like every calculation I do, I'd say 40% chance it's wrong. So, you know, it's helpful to me if you sort of keep an eye on my calculations. I slip a lot of negatives and make a lot of arithmetic errors. I try not to, you know, but what this calculation tells you that's interesting is, I don't know, like that doesn't look like a horribly odd way to rig a system up, but when you calculate those forces, you see that you're expecting that cable to hold a lot of force compared to the pin, which would be relatively stronger in most cases. You know, it's a like a metal bar as opposed to some kind of rope or cable. And so that starts to hint at where you might have failure of a system you put together. You know, do you have a cable that can withstand that? And if you're planning to build this thing, you have to make sure that you have a cable that can withstand that. And in order to know that, it leads into one of the classes that you'll most likely take in the spring, deform. Okay. Any questions overall on this problem?
And number 2, you have BTYs is 1680.1.
Yeah. Mhm. Okay. So now I want to say something. I think I mentioned it once before, but I want to get something formally in your notes on statically determinate versus statically indeterminate. As opposed, it's determinate instead of determinant. Notice that. Because you always look smarter if you spell stuff right. Just like, so when you're at the U or wherever you're going, when you go talk to, when you turn in homework, make sure stuff like that is spelled right. When you go talk to your professor, make sure you have a free body diagram to show him or her. Like, those two things will like make such a difference in how you're viewed, in my opinion. Okay, so each free body diagram that you draw, if you're doing a 2D problem, you can get three total equations out of the free body diagram, right? For if you're isolating a rigid body. If you're doing a 3D problem, you get 6 useful equations. What that means is if you isolate a free body that has more unknown loads than that, more variables need to be used to represent your loads, you can't solve it, right? It's a simple idea. So if more variables than that are necessary, then your body is statically indeterminate. You just can't solve for it. Like, don't allocate yourself more time to fiddle with the algebra. You can't solve it, you know? So that's called statically indeterminate. And let me give you an example of a statically indeterminate system. Okay, so you have this beam, it's connected to the wall, and it's supported by a roller. Say each of these lengths is 1/2 a meter. And you have a force acting down of 50,000 newtons. And say you want to calculate the reactions. The free body diagram then looks like this. You have this known force of 50,000. What kind of load do you have here at the roller?
Fly only.
That's right. So I'll call that, just call that R. And what kind of load do we have here at the wall? Full force and a couple, because it's a fixed joint. So I'll call this the force on the body by the wall, and I'll call this the moment on the body by the wall. Okay. So right now you can see, like just count up the variables. We have 1, 2, 3, 4 variables. We're going to get 3 equations out of it. So based on what I just said here, we can't solve it. But I want to go through this. I want to use this as a demonstration of one thing you should notice. It'll just simplify things a little bit occasionally. So let me move this over. And let's fill out the table. I'll put the coordinate system, where did I put it? Here. And I also made that my about point. So there's where the force is applied, about point, rho, force vector, and the moment about A. So let's start with that couple. So that's applied at 0, 0. We're going to choose an about point at 0, 0, but let me leave that out actually to show that that's not important for the couple, right? That couple is just going to get added on no matter what our about point is. And our couple then is just MBW. Okay. And then FBW, that also is acting at 0, 0. About point 0, 0. So rho is 0, 0. The force is FBWX, FBWY, and the moment is 0. R, that's acting at, well, where is that acting? We know that the X component is positive 0.5. What's the Y component? I didn't give any thickness of this thing, right? So I'm just going to call that negative H1, okay? Or maybe T1 would be better for thickness. Well, I'll leave it like that, okay? You follow why I did that there? I mean, we could put a number in there if I had told you the thickness of that beam was 1/4 of a meter or something.
1/2 H1.
Well, yeah, I mean, let's just call it H1. I mean, the about point is 0, 0. So rho then is 0.5 negative H1. The force vector is 0, R. And so the couple is 0.5 R minus 0 times negative H1. So we got lucky there, right? That unknown H1 disappeared, and it's not going to show up in any of our equilibrium equations. Okay? And now this 50,000, okay, so let's do the same thing over here. That's acting at 1, and then I guess negative H1 again. In my example on here, actually, I applied it at the top, so it was an H2. Anyways, forget that. So 0, 0 is the about point. Rho is 1, negative H1. And this force is 0, negative 50,000. And is it too much to hope for that we're going to get lucky again and that H1 is going to disappear again? No, it's going to again. So that's the fact that those both disappeared is something that I'm gonna, like after I go through, like this is supposed to be an example of statically indeterminate, but at the end of this problem, I'm gonna give you a general rule for why those H's disappeared that's gonna simplify problems for you a lot of times. So you should look for cases where you can use this fact. All right, Newton's second law says F BWX F BWY plus 0R plus 0 negative 50,000 is equal to 0, 0. And the rotational version says MBW plus 0.5R minus 50,000 is equal to 0. Okay, so we just followed that all the way through, got our 3 equations, and we see why having 4 variables was a problem, right? We have 3 equations, 1, 2, 3, 4 variables, and so there's nothing we can do at that point, okay? So I have a question about what this means, okay? Statically indeterminate means there's mathematically no solution. But, I mean, you could build this thing, right? I mean, you could glue this beam to the wall and put a roller underneath it, and, like, it won't create a black hole or something, you know, like, something will happen. You could put load cells in those locations and measure forces, right? And those forces would be consistent. You know, it would happen over and over again. It's not like there'd be some kind of singularity. So what's the deal? Why can't we calculate this using statics? And how would you calculate this? This is a question for Joe back there. And Alan, who's sleeping still.
You'd have to look at the properties of the beam you're using.
That's right, exactly. So how those loads are distributed across those 2 different joints then is determined by how flexible that beam is. And so in order to get the extra equation that you need in this case, you have to use how the beam's going to deform. And that's the kind of thing that we do in deform. Okay, so like we could do this problem using the methods of deform, but using just the methods of statics, there's nothing we can do if you have a statically indeterminate system. Okay. So you'd have to know some properties, additional properties of the material. Is it steel? Is it silly putty? Those two things would distribute those loads in different ways. Although if you applied 50,000 newtons to silly putty, it probably isn't going to hold very long. Oh yeah. That was my thesis. And when you take it off, if the wall has newsprint on it, you can read it on the silly putty. Yeah, backwards, in a mirror. So you'd have to know additional material properties. So we'll revisit that topic in deform, but for now, you can save yourself time if you add up the number of load variables you have before you start filling out that table. You know, make sure that you have the right number of variables. All right, and now here is the thing that I was getting at with these H1s. Notice that variable H1 didn't come into the equilibrium equations. And why was that? Because of the following rule for rigid bodies. In any rigid body, and that is equivalent to saying in any free body diagram you draw, you can move the location of your force, okay, that P, that point P, for any force anywhere along its line of action. Without changing the problem. Or maybe I should say without changing the results. So for example, if your problem originally is this, okay? The line of action goes through that point. That doesn't look parallel, does it? Am I being too anal here? Okay, so the line of action goes through the point where the load really is applied and is parallel to that force. So you could apply the force here if you want. Okay? And that's what was happening here. that H1 didn't come into this problem because it doesn't matter. Like, this problem will give you the same results as if this force R was applied at the middle of the beam or above the beam or whatever. Okay? So we could have just as well treated this load R as if it was applied at 0.50. Okay? And that's something to look for. That can make things simpler sometimes. But I want you to notice one thing that also is sort of a setup for deform. This isn't true like, how do I want to say this? This isn't true for non-rigid bodies. So when you, like, okay, let me draw the silly putty again. So for example, think of silly putty, okay? And think of what would happen if you applied a load here to silly putty, and what would happen, it's supposed to be the same thing, if you apply the load here, okay? That silly putty is going to deform in a totally different way based on where you apply that load, okay? So this trick only works while you're treating something as a rigid body. And in deform, you'll treat something as a rigid body to do one calculation, then you'll look internal to that, and when you have your body isolated, you're treating it as a rigid body. When you look inside, you're not. So anyways, it's something you'll have to be careful of in deform. But for now, anything that we do, you can just feel free to move those forces along their line of action for whatever makes the moments easier to calculate. Okay. I wanted to do one more, have you guys do one more problem. Maybe maybe I'll just do this one. So let's do one more example. No, you know what? Why don't you, I'll give you the problem. Think about it, talk to each other about it. If you have time to think about it outside of class, do it. And when we come back, I'll just do it first thing in the next class, okay? Okay, so say that you have an 80 kilogram person. Okay, this, I'm going to give you a very strong suggestion of how to treat this part. That's he's holding this roller thing. Okay, looks like Raggedy Andy. Mass of 80 kilograms. And let's say in this position, his center of mass is right here. That distance is 1/2 meter. And that distance is 1 meter. And this height from the floor to where that roller touches the wall is 0.8 meters.
That's the same as the center of mass height too?
You don't need that in this problem.
Okay. No, okay.
So I want you to try to figure out what are the reactions at the points of contact between the floor and the wall and the person. And second, what's the coefficient of static friction required at the shoes for him to stay up?
So reactions on wall and floor, you're saying?
Yeah. Okay, so for the next 5 minutes, why don't you just think about that? Try to sketch out a plan for solving this. And then when we come back next time, I'll go through the solution.